This video is brought to you by mywayteaching.com.
In this part, let us study energy of the orbiting satellite. See, the kinetic energy of the satellite in a circular orbit with the speed v is given by half mv square. So that is equal to gmme by 2re plus h if you substitute v. Considering the gravitational potential energy at infinity to be zero, the potential energy at a distance re plus h from the center of the earth is given by minus gmme by re plus h. So the kinetic energy is positive whereas potential energy is negative. Okay. However, in magnitude, the kinetic energy is half of the potential energy. So we can write the total energy is equal to the sum of the kinetic energy plus potential energy, which is given by minus gm me divided by 2re plus h. So the total energy of an circularly orbiting satellite is thus negative, with the potential energy being negative but twice its magnitude of positive kinetic energy. So when the orbit of a satellite becomes elliptic, both kinetic energy and potential energy they change from point to point. The total energy which remains constant is negative as in circular orbit case. So satellites are always at a finite distance from the earth and they have energies that cannot be positive or even zero. Okay. Now let us see a very simple problem. A 400 kg satellite is in circular orbit of radius 2re about the earth. How much energy is required to transfer it to a circular orbit of radius 4re? So, what are the changes in the kinetic and potential energies? So, this is the question. Let us find the solution for this. So, initially, that energy is given by EI, that is minus G MEM in by 4RE. Okay. And finally, it is given by EF, that is minus GME M divided by 8RE. So a change in the total energy is given by delta E, that is equal to EF minus EI, isn't it? So if you do EF minus EI, we get G ME M by 8RE, that is also equal to GME by RE square into MRE by 8. So we know this represents acceleration due to gravity, that is G MRE by 8. So substituting the values, 9.81 m is given by 400 kg, re, that is radius of the earth, 6.37 into 10 raised to 6 divided by 8, that is equal to 3.13 into 10 raised to 9 joules. So the kinetic energy is reduced and it mimics delta E. So delta K, that is Kf minus Ki, is also equal to 3.13 into 10 raised to 9 joules. So the change in potential energy is twice the change in total energy. So that change we can write it as delta Vf, that is Vf minus Vi, that is equal to minus 6.25 into 10 raised to 9 joules. Okay, this is the value for the change in potential energy, the change in total energy, change in kinetic energy, and change in potential energy. So now let us study geostationary and polar satellites. See, an interesting phenomena arises if we arrange the value of Re plus H such that T in the equation, that is T is equal to 2 pi Re plus H whole raised to 3 by 2 square root of GME. Okay, if this equation becomes equal to 24 hours, if the circular orbit is in the equatorial plane of the earth, such as a satellite having the same period as the period of the earth about its own axis, would appear stationary, which is viewed from the point on earth. So Re plus H for this purpose works out to be large as compared to Re. So in that case, Re plus H is equal to, if the revolution on its own axis, if it is similar to that of the earth, then it looks stationary when we look from the surface of the earth. So Re plus H is equal to T square GME by 4 pi square whole raised to 1 by 3. So for T is equal to 24 hours, if we want T is equal to 24 hours, H works out to be 35,800 kilometer, which is much larger than Re. Satellites in a circular orbits around the Earth in the equatorial plane, if T is equal to 24 hours, they are called as geostationary satellites. Okay. Since the Earth rotates with the same period, the satellite would appear fixed. Okay, if you watch from any point on the earth, it it remains fixed because it rotates with the same period as that of the earth. So it takes very powerful rockets to throw up a satellite to such a large heights above the earth, but this has been done in view of the several benefits of many practical applications. So it is known that the electromagnetic waves above a certain frequency are not reflected from the ionosphere, isn't it? So radio waves used for radio broadcasts, which are in the frequency range of 2 megahertz to 10. Okay, are below the critical frequency. They are therefore reflected by the ionosphere. So thus radio waves broadcast from an antenna can be received at points far away where the direct wave falls to reach on account of the curvature of the earth. So waves used in television broadcast or other forms of communication have much higher frequencies than, thus cannot be received beyond the line of sight. A geostationary satellite appearing fixed above the broadcasting station can, however, receive these signals and broadcast them back to the wide area on the Earth. The INSAT group of satellites sent up by India are one such group of geostationary satellites widely used for telecommunication. So, usually, this telecommunication purposes for telecommunication purposes only, we'll go for geostationary satellites. So another class of satellites are called as polar satellites. So as you can see in this figure, these are low altitude, which means H is equal to say 500 to 800 kilometer satellites, but they go around the poles of the earth in a north and south direction, whereas earth rotates around its axis in an east west direction. Since its time period is around 100 minutes, it crosses any altitude many times a day. So the time period is just 100 minutes, so it crosses an altitude many times a day. However, its height is between 500 to 800 kilometer. A camera fixed on it can view only small stripes of the earth in one orbit. Adjacent strips are viewed in the next orbit, so that in effect the whole earth can be viewed strip by strip during the entire day. So these satellites can view polar and equatorial regions at close distances, so with a good resolution. So they are mainly used to view these polar and equatorial regions. Okay, so information gathered from such satellites is extremely useful for remote sensing and even in meteorology as well as for environmental studies of the earth. Coming to the last concept, that is weightlessness. See, weight of an object is the force with which the earth attracts it, isn't it? It is nothing but the force that is exerted by the earth on that particular object. We are conscious of our own weight when we stand on a surface, isn't it? The surface exerts a force opposite to our weight to keep us at rest. The same principle holds good when we measure the weight of an object by a spring balance hung from a fixed point, for example, in the case of ceiling. The object would fall down unless it is subject to a force which is opposite to gravity. So, this is exactly what this spring exerts on the object. So, this is because the spring is pulled down a little by the gravitational pull of the object, and in turn, the spring exerts a force on the object vertically upwards. See, now imagine the top end of the balance is no longer held fixed to the top ceiling of the room. Both ends of the spring as well as object move with identical acceleration g. The spring is not stretched and it does not exert any upward force on the object which is moving down with an acceleration due to gravity, that is g. The reading recorded in the spring balance is zero since the spring is not stretched at all because it is not fixed at the top. If the object were a human being, he or she will not feel his weight since there is no upward force on him. So, when an object is in free fall, it is weightlessness, means it will not experience that pull. So, this phenomenon we call it as weightlessness. In a satellite around the Earth, every part and parcel of the satellite has an acceleration towards the center of the Earth, which is exactly the value of Earth's acceleration due to gravity at that position. So, in that satellite, everything inside it is a state of a free fall. This is just as we were falling towards the Earth from a height. Thus, in a manned satellite, people inside experience no gravity. Gravity for us defines the vertical direction, and thus for them there is no horizontal or vertical directions. All directions are same. So, pictures of astronauts flowing in a satellite are because of this fact, because they experience no gravitational pull. So that particular situation is called as weightlessness.